Let's talk about electrolytes and non-electrolytes. We need to touch on this so you guys can finish up the homework number 10. So here's basically a little rig that you can kind of establish. So we have this battery here, and the battery is going to be transferring electrons or electricity to the bulb. Now, if the lines of these electrodes are actually crossed or they're touching, then you're able to sit there and get electricity flowing through and the bulb will light up. If the lines aren't touching, right, there's no transfer of electrons between them, then it's going to be dark. Now, we can do this also in terms of, have you guys ever seen the somebody stick electrodes into an apple where the apple causes the light bulb to turn on?
I saw them do that with lemons.
With a lemon?
Mm-hmm.
So why do you think that's the case? Why do you think that worked in the case of lemon?
Well, since I have the acid-base topic, I know a little bit more about this is because acids can conduct electricity.
Because of what? Why do you think they conduct electricity? Because of the ions, exactly. Acids are just an example of an ionic reaction, right? You got a plus charge and a minus charge. And because they're separated, depending on the type of acid we're working with, they have that plus and minus charge. It's able to sit there and conduct electricity, okay? So that brings us to this topic right here. So if we have what we call electrolytes. Electrolytes are basically the formation of ions that are able to conduct electricity, right? So strong electrolytes are able to conduct electricity pretty strongly. So we get a nice little bulb going on. A weak electrolyte conducts very weakly, right? So typically these are like, let's say weak acids or weak ions, you know. So in that case, these guys aren't going to conduct as well because they're not all broken up in high concentrations, where a strong acid or a strong ion, you know, is able to separate completely. And then you're able to sit there and use those charges to get alignment and to get electrons passing through. Where something that is non-electrolytic, such as ethanol or water or things like that, they're not able to sit there and pass through those electrons. Electrons aren't able to sit there and flow through it. They'll orient towards those axes, but they won't actually transfer the electrons because they're covalently bonded. They don't have that ability to sit there and form the ions themselves, okay? So in the case of, let's say, why is it that, let's say somebody throws a toaster into your bathtub? Anything like that ever happened to you?
I mean, I don't think I would live to tell the tale.
Okay. Okay. So what happens? Why do you get electrocuted? What's happening in the situation in that case?
Well, the electricity, I guess, is using the water as it's like spreading across the water, and then, you know. Yeah,
it is spreading across the water, but you're acting as those electrolytes, right? Because in you have like that sodium ion, you have that potassium ion, and so it's flowing through you. And since that electricity is flowing through you, you're able to get a little bit of a nice shock going on there. You know?
I guess it's a little bit of an understatement, but so I'm trying to find a way to like phrase this question. So you get shocked because we have electrolytes in us. It's not that just we're in the water and we just get shocked.
Yeah, well, the water itself doesn't conduct electricity, right?
Oh.
It isn't able to conduct electricity, but you are, because you do have those electrolytes in you, right? You have those ions that are available to sit there and pass on those, you know, so electricity will flow through you. Mm-hmm. Not well, but it does flow through you. Okay.
Okay.
Okay, so an electrolyte. Okay, so electrodes are basically, they're conductors by which electronic charges are able to enter and leave. Okay, so electrolysis is just the passing of electrons through electrolytes. So the fact that we're making those ions are serving as a means of passing those electrons. Okay? And then the ability of a solution to conduct electricity is basically gives us as evidence that there's ions available, right, for that conduction, right? And so this is basically how it works. If you guys take a look. So here we have a solution of potassium iodide. So that's in water. So the water allows the potassium, not potassium iodide, potassium chloride, that's in water. The water will allow those ions to separate into their ionic components. Because those ionic components are going on, so then you're able to sit there and get those plus and minus charges that are going from post to post. The minuses are trying to get over to that plus, and then the plus is trying to get over to the minus. And so they're able to sit there and carry those electrons across as a result of that. And so the electron is able to flow through the solution because of those ionic charges. Okay, can you guys see that?
Yes.
Okay, so again, something that's a strong electrolyte is able to sit there and first off, when it's in water, it dissolves completely. You have complete dissociation. So in that case, you have very few of them that are still connected together, right? So those plus and minuses are separated from each other. And so those are considered to be a strong electrolyte, where a weak electrolyte only dissociates a little bit. So most of them are still connected. You only have a limited amount of them that are dissociated. And then a non-electrolyte won't dissociate. Water doesn't dissociate, right? You don't get a H plus and a OH minus, right? Technically you do a little bit, but not enough to sit there and do anything. And that's the same thing with, let's say, ethanol. Ethanol isn't going to dissociate. You're not going to get those plus and minus charges that they don't occur. Okay, so if we take a look at sodium chloride, if we add sodium chloride to water, it's going to completely dissociate, okay, into its two ionic components, and then we just put Na plus, aqueous, and Cl minus. Okay, the same thing with copper 2 chloride, right? So in this case, we'll get copper 2 plus, aqueous, and 2 Cl minuses. Now, why are we getting 2 Cl minuses? Why don't we call it, can you guys see my screen? I'm just talking.
We could see it.
Okay, good. So why don't we write it like this? Anybody want to take a guess?
To show us maybe that the chlorine is an ion, not just a diatomic element.
That's right. So the chlorine is an ion, and it's not a diatomic element. Now, what's going to hold that compound together is the fact that they're plus and minuses charges. Soon as you separate those plus and minus charges by using water, right? So you no longer have that chlorine ion connected, to the copper. It's able to go freely. So each of them are able to go freely. You guys get that? So like the copper is what holds that Cl minus and that other Cl minus together onto that complex. So as soon as we separate them, then they're able to go freely. You guys get it, right? Yeah, no, maybe?
Why does it hold it together?
Because it's charges, right? The plus, that plus charge.
Oh, okay.
Yeah. So without them being able to interact with each other, the fact that water is the home wrecker separating that couple, right? So then the copper is being surrounded by water, and then the Cls are being surrounded by water. So each of those Cls are being surrounded independently, right? They're not connecting, they're not interacting with each other. Because if you have two negative and negatives, what is going to happen?
They're going to go away from each other.
They're going to go away from each other. there's not that positive to bring them together, right? They're going to repel. Okay, so here's an example. So if we're dissolving salt in water, sodium chloride in water. So first, initially when you put it all in water, you have your plus and your minus, your plus and your minus, your plus and your minus. But as we notice, as it sits in that water long enough, it'll actually dissolve, right? The water will actually orient itself so that the hydrogens will be interacting with the minus charge and the oxygens will be interacting with the plus charge, okay? That's because water is polar, meaning that it's partially positive and partially negative. Even though it's a single compound, it's connected together, but it has that partial charge that's associated with it. And so oriented as such. You guys remember that? I think I've drawn it like 150 times. Maybe 200. Remember that? Partial positive, partial negative. Yeah, because it's partial, right? It's going to sit there and surround. The oxygen is going to orient towards the plus charge. The hydrogen is going to orient towards the minus charge. Okay. So same thing is going to happen with the copper 2 chloride. So then water is going to sit there and orient itself around the copper 2 ion, and then each of the chlorides are going to be surrounded by water again, but in that case, you're going to have oriented towards the hydrogens of the water molecule. Okay, simple, simple. Okay. Come on. Are you guys seeing my big screen or my big screen? Okay, so write the dissolving equation for potassium sulfate. So what am I going to do? So I'm writing my chemical equation for potassium sulfate as it dissolves. So what am I going to get? What are going to be my products? Norma, what are going to be my products, Norma? Are you there, Norma? Can unmute yourself. Okay, Cheyenne. Norma's being shy.
Okay, it's going to be K and then plus the SO4.
K plus SO4. Are there going to be charges associated with it?
Oh, yeah. Hold on. SO4 is a 2 minus.
Okay.
And K is a plus. So you would write a 2 in front of the K, right?
That is correct.
But do we always have to put the H2O at the top of the arrow?
You don't always have to do it. You could also say plus H2O over here.
Oh, okay.
Yeah. But if you notice in your homework assignment, kind of have it understood. Well, if you guys have already started your homework assignment, it's already understood that when you're dissociating, it's kind of like having that arrow with the H2O. So you're not actually putting it in the equation.
Okay, thank you.
No problem.
Can you explain again why K2 turns into 2K plus?
Okay, again, because the reason why these guys are interacting with each other, right? The sulfate and the potassium is because of the charges.
Mm-hmm.
This basically means that you have one potassium here, you have your SO4, and another potassium. That's what that's meaning, right? Soon as we separate them, soon as we add water to them, it's going to separate into two independent. You're just going to get a potassium that's going to be surrounded by water.
Oh, so there's no bond between the two potassium atoms? Is that why it's not K2?
The bond that we have is there's no covalent bond. It's an ionic.
Oh, okay.
And ionic bonds are just, when they're solids, they're interacting with each other. But as soon as you put water in there, or you put some type of solvent in it, it's going to be able to dissociate. Okay.
Okay.
And then you're just going to get those ions separated. It's kind of like, let's see, I'm going to give you an example. Yeah, I can't think of it. It's kind of like Velcro, right? Because you have that piece of Velcro, they stick together, but you can pull them apart, right?
Yes.
So it's just like Velcro.
Yeah. I just need to remember that it's not a covalent bond. I think that's the key part there.
The sulfate is covalently bonded. So that's why it doesn't separate independently. You don't get sulfur and oxygen independently because they're covalently bonded. It takes a lot of energy to separate. Okay. Now what about, let's see, write the ions present in the solution for calcium nitrate without writing a dissolving equation. So what are the ions that are going to be in a calcium nitrate solution?
Calcium and nitrate.
Okay, so that's chemical formula.
Ca, and then that has a 2+ charge, and NO3 has a -1 charge, so that's why you need 2 to balance.
NO3, so then there would be 2 of these guys just kicking it.
Right.
Okay. Good. Simple, right?
Mm-hmm.
Clear.
Is there a difference between writing the 2 for the nitrate? Is there a difference between writing the 2 as a coefficient versus a subscript for that?
Yes, it's wrong if you write it as a subscript.
Oh.
Yeah, because it's separated. Again, it's that plus and that minus, right? As soon as you disrupt that plus and minus, they're going to separate. They're going to be independently. They're going to act independent of each other.
Mm-hmm.
You understand? But if you write them together, you're saying that they're covalently linked. They're bonded together. That's not the case. They're separate.
Nitrate?
The nitrate. So the nitrate is going to, each of your nitrates are going to be independent of each other. They're not, They're not covalently bonded together. If you write it as NO3, that's wrong.
Mm-hmm.
Okay, because they're independent of each other. The only thing that's holding them together, because you have 2 minus charges that are coming together, right? So what's going to happen again if you put 2 minuses together?
They're going to repel.
They're going to repel. So that's not going to happen, right?
Mm-hmm.
And so in solution, they're not going to do that. They're going to repel. They're going to go as far away from each other as possible.
Oh, got it. Okay. That makes sense.
The only thing that's going to bring them together is somebody who's positive, like me, you know. I bring you guys all together.
Got it. Okay.
Okay. Substances that have a proton can, let's see. Okay, so acids. Let's talk about acids. I was just going to read the screen. Crazy. So we've been talking about acids. Acids are basically what we call a proton donor, right? It donates a proton, which is an H+, right? Because we know that H+ is only a proton, and I can spell it out for you 50 million times, but we know that H+ only has a proton. That's it. So it's considered to be a proton donor, okay? So we've been talking about acids almost since the very beginning of the course. So you guys should be pretty familiar with acids. We also talked about neutralization reactions, right? Where you're donating that H plus and you're gonna end up making water, right? So if we put acids in water, the first thing that they're gonna do is separate into their ions, right? So this is an example. This is the generic form of an acid. So HX plus H2O is gonna give us the hydronium ion and that negative charge, that anion that we're gonna get, right? And so here we have hydrochloric acid. We put it in water, we get the hydronium ion, and we get our HCl. Now, often we just write this as H plus because it's a lot prettier to look at. AQ. And Cl, oops, not Ag. AQ. And so that would be the equivalent of this. So these are exactly the same thing. Okay? Are you with me?
Yes.
Okay, good. So if we have nitric acid, the same thing is going to happen. We'll end up with our nitrate, AQ, and our hydronium ion, which we also will just write as H plus, AQ. Piece of cake, simple, not too hard. And so often you'll see them written both ways, but really this is what the hydronium ion looks like, because that H plus is going to really bind onto water. It's going to be like, ooh, I love you. I love you, I love you, I love you, right? It's very needy. Okay. So these are some other examples here. This is where we have sulfate. Now sulfate has it's called polyisoprotonetic, meaning that it's able to give 2 protons, right? So it's able to get rid of that very first one, and then it's able to get rid of that second H plus, okay? So here, you're getting rid of that very first one, and then you have hydrogen sulfate, and then that hydrogen sulfate can be broken down further, and it's able to give up its H plus 2, and then so you're just end up with the sulfate ion. Okay. Are we good? Okay. So all of the acids that we've talked about, a lot of the acids that we've talked about and that we made emphasis on have been strong acids. Now there are weak acids as well. All carbon-containing acids are weak acids. Do you want to repeat that? All carbon-containing acids are weak acids. Okay, you want to repeat that one more time? All carbon-containing acids are weak acids. So, does this acid contain carbon? This is acetic acid. Alan, are you there?
Yep.
Does this acid contain carbon?
Yep.
Okay, is it going to be a strong acid or a weak acid?
It's going to be a weak acid.
It's going to be a weak acid. Okay, now, since it's a weak acid, we're going to draw arrows going both directions because both moieties are going to exist. In all honesty, we should kind of draw it funny so that it's more like this, where you have a fat arrow going one direction and a skinny arrow going another direction, like that, or a longer arrow going one direction and a skinny arrow going the other direction, because you're going to have one side favored. And that side that's going to be favored is the one where your H plus is still connected to the acid moiety, right? Or in this case, the acetate. It's still bonded to the acetate. So you're going to have more of these guys present in solution than you're going to have them separated. Okay, so this kind of brings us to a new term, what we call our major species and our minor species. In a strong acid, this being a strong acid, Sulfuric acid is a very strong acid. Now, sulfuric acid is going to completely dissociate. That means you're going to get complete dissociation in both cases, so that you're ending up with just your sulfate, and you're going to end up with your 2 H pluses, right? So it's going to completely dissociate. So it's going to favor the other side. It's going in only that one direction. Okay, so then in that case, our major species would be the ions. So I'm going to write this generically as H2SO4, AQ, okay, what does major mean to you? If you have a major in chemistry and a minor in theology, what does that mean?
It's your concentration.
It's your concentration? Okay. So if I say something is major, the major component in soda is water, and the minor component in soda is acid. What does major mean? Steve.
Can you repeat that again?
I said, if the major component in soda is water and the minor component is acid, what is the major component? What does major mean in that case?
Can you say the most important, like it has the biggest effect on it?
The biggest effect or the biggest amount?
Biggest amount.
Okay. Okay. So when we're talking about major species and minor species, major species makes reference to the one that you're going to see most commonly, the most abundant in the solution. So in a strong acid, such as sulfuric acid, your ions are going to be your major species. And your minor species is going to be this guy. Minor meaning that you don't see a lot of it. Major, you see a lot of it. Okay? So in a weak acid, your major species is going to be this guy.
I have a question. What do you mean you don't see a lot of it? Don't see a lot of it in what?
In the solution. Because
okay.
In a chemical reaction, you don't always get 100% separation. This guy here, this guy is about 99.9999% separation.
Oh, okay.
Okay. So that 0.0001%, right, does exist, but it's very little. Okay. Now your major species here in this acid is this guy. Okay. This here's your major species.
Is there a way that you can tell if it's major or minor?
Yeah. If you know if it's a strong acid or a weak acid. If it's a carbon acid, it's a weak acid. And I'm going to give you some examples of weak acids. And I'm also going to give you examples of strong acids.
Are those the only like markers that we need to like look out for, or are there more?
Those are the major markers.
Okay.
Yeah. Wait, I'm confused. Did you say that if it has a carbon containing acid that it's what is that? Acid. Major, right? It's a weak acid, but is that considered major?
No, or? It's the acid itself, the H and whatever that acid is, the H in this case acetate. This here is the major component, right, where the ions are going to be the minor component. Meaning that, in other words, in a weak acid, these guys are going to stay together more than they're going to separate into their ions.
Okay.
Okay?
Sure.
Just for right now, nod. Don't worry, we'll get more into it, I promise. Just nod for right now, and then ask me the question in 5 minutes.
Okay.
Okay? Okay, so strong acids, they're going to completely ionize. Ionize is what we use in terms of forming ions, right? Or splitting up into their ionic components. So strong acids completely ionize. They separate completely. They separate into their 2 ion forms. Or almost completely, okay? So, like I said, in this case, sulfuric acid is going to be 99% of it going to be like this, 99.999. And then you're going to have 0.001% is going to be in this form, them together, okay? Okay, now strong acids, they conduct electricity strongly, so your light is going to be really bright, and then you're going to see mainly the ions. So like a large percentage is going to be the ion. Okay, your minor species is going to be the unionized form. This is unionized, meaning that it's not broken up into its ions. You got it? Okay. Now, weak acids are only going to be slightly ionized. So that means that the majority of the species is going to be unionized, and only a little bit, the minor species, is going to be ionized. Okay, so let me show you an example. Okay, so strong acid, this is hydrochloric acid. Here, we have chlorine, and then we have, this is our hydronium ion right here. That's our H plus that's connected with water. So, or H3O plus, okay? Okay, so these are our hydronium ions. You can see that they're completely separated. You don't see any of them together, right? So those are going to be strong electrolytes because it's going to completely dissociate. Where acetic acid, this here, that's acetic acid. That is that HC2, H3, O2. Okay, so, and then you see in our solution, the majority of them are acetic acid. They still have that H connected, and only a few of them are the ions. So you have one hydronium ion here, that's your H3 plus. I'm sorry, H3O plus. And then this here's your acetate. So that's C2. Okay, where you have the majority of your species. Let me put this in a different color. Circle these in green.
I had a
where
question.
The majority of our species are still connected. Do you see that? Are you with me? Yeah, no, maybe?
Can you be a weak acid and still be major?
So major only refers to species, right? So either you're going to be, your major species is going to be the acid being together, or it's going to be the ions. You understand?
Mm-hmm.
So major refers to our species. So either you're going to have, like here, your ions are your major species. Here, your acid is your major species.
Oh, okay.
Do you understand? So in both cases, you're always going to have, every equation is going to have a major and a minor species. So they're favoring the product side or favoring the reactant side. You understand?
Yeah.
in this dissociation reaction.
I'm kind of confused then, because I asked you like, oh, how can we tell if it's major or not? And you said, well, if it's a strong acid.
If it's a strong acid, HCl is a strong acid. HCl is going to always dissociate into its ionic components. Now, think about what you asked me. So it's just going to write it H plus instead of. Okay, so what is the major species for hydrochloric acid?
Is it the reactant side?
Nope. Strong acids always are going to dissociate to their ions. That means that which one is going to be existing more? Is this side going to be existing more, or is this side going to be existing more?
The product side is going to be existing more?
That's right. So you're going to have about 99% of this.
And that's because it has dissociated?
Because it's dissociated.
Oh,
so
okay.
It's going to dissociate. Dissociation, right? So things are going to dissociate. But the question is, how well do they dissociate? So a strong acid almost dissociates completely. A weak acid.
Oh, this is making more sense to me now.
Okay.
So
a weak acid doesn't. A weak acid will stay together. Now here, this is. I'm just gonna still this. Hold on.
So a weak acid. I'll try to phrase this in like a way that makes sense. So in a weak acid, there's gonna be some atoms that have dissociated, but there's going to be a lot more molecules than there would be in strong acids, because
that's right. Yes.
Okay, makes sense. It's just a lot to keep track of.
And you guys have had a week of non-science, so that doesn't help. Okay, so this is a weak acid, right? A weak acid, and let's talk about major and minor. This is major. And this is minor. So weak acid, it's going to favor the reactants, right? Meaning that you're going to have more of these guys in solution, which is what we're showing here. 1, 2, 3, 4, 5. We have 5 of those in solution compared to over here where we don't see any of those that are connected together. You see any HCl in this solution at all? The green represents.
No, I don't see any.
You don't see any, right? So here, where you have the hydrogen attached to, just that hydrogen molecule attached to this ball thingy, right? So here, these guys are still connected. You have a large percentage of those that are still connected. That represents our acetic acid molecule, right? So in this case, our major species is
that's our major right there.
That's our major here. That's right. And then our minor
are the ions.
Okay. Questions?
So
Cash.
Yeah. Is the only way that you can tell whether or not it's a weak acid or a strong acid is whether or not it has carbon in it? Is that the only?
Well, that's not there are a couple of them that are going to be weak acids. And I'm going to tell you about those here in a second. I promise.
Okay.
Be patient. The one that is so far that I've only talked about are things that have carbon in it. All carbon containing acids are weak acids. So carbonic acid, a weak acid. Acetic acid, a weak acid. Citric acid, a weak acid. Okay?
Mm-hmm.
And that's partially part of the reason why it doesn't kill us when we eat citric acid or we eat acetic acid or ascorbic acid, because they're all weak acids. You know? Otherwise, we wouldn't be having those lemonades and things like that. Okay? Questions, concerns? Cash. So is that a little bit clearer now?
Yes.
Yeah.
Okay. So I like it when I get 2 yeses. That means we're making progress. It's not just 1 yes. Now, when I get 12 yes, I may pass out, you know. Okay. So this is just showing you examples of strong acids and weak acids. Now, hydrofluoric acid. Hydrochloric acid is a strong acid. Hydrofluoric acid is a weak acid, right? And you're going to ask me, you're like, yeah, why is hydrofluoric acid a weak acid? You know, aren't hydrochloric acid and hydrofluoric acid almost the same? Well, no, they're not. The reason why hydrofluoric acid is a weak acid is because fluorine. Fluorine is, I think we talked about this a little bit. Remember I told you he's the bully or the abusive boyfriend? Mm-hmm. Okay, so fluorine is kind of like that abusive boyfriend, right? It gets with hydrogen and it's like, no, you're not leaving me. You keep your ass right next to me. You cannot go anywhere. Can't go to the bathroom without me. You can't go anywhere without me. No, you can't hang out with your friends. Nope, you keep your butt right here, right? Very abusive boyfriend. So fluorine wants that plus charge so much, right? It keeps it at bay. It takes that ion and makes sure that you stay close to it, right? And it isn't going to let you go until he dumps you for somebody else. That's the only time that he'll do it, okay? So he's always going to stay together. Where chlorine is kind of like, hey, okay, yeah, we're in water now. You do whatever you want to do, right? I have water. Me and water are tight. You know, we mess around, you know, so you can do whatever you want to do. Where fluorine isn't like that. Fluorine is going to try to stick together. So in that case, go ahead.
So that means that it won't want to dissociate then because it wants to stick with the hydrogen?
That is correct. And so it's going to be a weak acid.
Okay.
So hydrofluoric acid is a weak acid, where hydrochloric acid is a strong acid. Okay. And this just kind of shows you that, right? So strong, weak. When you put in solution, this is how much ionizes. This is how much breaks up. So at a 0.10 molar solution, 79% of it breaks up. At 0.01 molar solution, molar means the concentration. So the higher the number is, the more of that acid that you have in it. The lower the number is, the less acids, the more water you have in it, okay? So 99% of it is broken up at a 0.1 molar solution. Now, hydrofluoric acid, only 9% of it is ionized. That's a very little, right? And then 0.01, only 22% of it is ionized. That's still very little. So this guy is great at conducting electricity. This guy is crappy at conducting electricity. Okay?
I had a question. Why, so fluorine, it doesn't want to let go of hydrogen because it needs that one electron, but so does chlorine.
Well, yeah, but the difference is that chlorine is bigger. Fluorine is smaller. And so since fluorine is smaller and it has everything really tight, it's going to be pulling that plus charge really, really tight. It's not going to want to let go. Kind of like little Napoleon, you know, like, no, you can't go anywhere. And so because of that size, the size difference between chlorine and fluorine, right? It allows a little more flexibility. So remember also we talked about that electronegativity?
Mm-hmm.
Okay. So first off, it pulls that electron. Not only that, now that it has that electron, since it's so small, it's still going to be having such a strong force, keeping that plus really tight to it. It's not going to let that plus go.
Oh, okay.
Okay?
Yeah.
Okay, so our major species are going to be the ions in the case of the hydrochloric acid. The minor species is going to be the hydrochloric acid itself, right? But in the case of the hydrofluoric acid, our major species is going to be the hydrofluoric acid, and the minor species are going to be the ions. Simple? Yay, nay, may?
Yes.
Okay, good. Okay, so these are the 7 most commonly well-known strong acids. Nitric acid, sulfuric acid, hydrochloric acid, hydrobromic acid, hydroiodonic acid, chloric acid, perchloric acid, okay? Okay, now as soon as you start putting OUS on it, that makes it a weak acid. So nitrous, let's see. Nitrous acid, it's going to be a weak acid. Sulfurious acid, going to be a weak acid. Chlorous acid, weak acid. Bromious acid, weak acid. Okay, so OUS makes it weaker. You got that, Kevin?
Yeah.
So that's another thing that we can look at to see if
Yep.
it's a strong versus a weak acid.
Yep.
Okay.
Okay. So we've already kind of talked about the major species and the minor species. So write the formula for the major species in solution of nitrous acid and chloric acid. So what would be the major species in solution for nitrous acid? Okay, what is the chemical formula for nitrous acid?
HNO2.
So are we going to favor the ion or are we going to favor the acid?
The acid.
That's right. So this would be your major species. That's it. Now, what about chloric acid? What is the chemical formula for chloric acid?
Sorry, I'm still writing this down, so maybe someone else can help you.
Somebody else can help me?
Is it HCl?
Is it HCl? I thought that was hydrochloric.
Yeah.
Oh.
Lauric acid. Let's see. Brian.
Is it HClO3?
That is correct. HClO3. Okay, so what's going to happen? What's going to be the major species? Is it going to break down or is it going to stay connected like this?
The major species is going to be in the product side.
Okay, so then the major species are going to be the H plus, AQ, or you'll often see, just in case, because you'll see them both ways on the exam, because I get lazy sometimes. Plus ClO, 3 minus. Okay. Simple.
And then that plus ClO3 would be next to the H plus 2 then, right?
Yeah. And I kind of like it writing the upper way because it's easier to keep track of the H, that H plus.
So when we're finding out the major species, we only. Oh, okay. I get it now. I was wondering why we were writing out the entire reaction, but since you erased the second part, that makes a lot more sense now.
Okay, piece of cake?
Yes. I was just confused because I thought that you were keeping the entire reaction, so I was like, well, how did we know what the major species is? But then
no, we were just writing it out.
Yeah.
I just wanted to see where we're starting from.
Yeah.
Can we do another example?
Sure. But that means you guys got to do the example. I just have to sit here and look pretty. So let's do. I'll give you the chemical formula. I'll be nice and give you a chemical formula. I won't just give you the name. So we'll do oxalic acid. And okay, so those are your two acids. What would be the major species for arsenic acid and oxalic acid?
For the oxalic acid, wouldn't it be the compound that you just wrote since it's major?
That is correct. Why?
Because it has a carbon, so it's a weak acid.
That is correct. What about arsenic acid?
I have a question. So, you said that acids that in an IC are usually the stronger ones, right?
Mm-hmm.
So I guess that'd be kind of confusing with oxalic acid.
But what did I say? What did I say before?
Yeah, that the carbons mean that it's a weak acid, so that's more important to look to rather than its.
That's right.
Its name,
it has priority. Yes, all carbon acids are weak acids.
Okay, thank you.
You'll learn there's a lot of priority in chemistry.
Oh, I'm already learning.
Okay. Arsenic acid. What does arsenic acid look like?
H3ASO4.
Okay. So, what are going to be the major species?
I feel like it would be the ions.
Okay. And what are the ions?
HNO2 or H2O?
H2O? Is it going to be H2O?
No.
What would be the ions from here? What would this break down into? Completely break down into?
Hydrogen plus oxygen 2 negative.
It's going to break down to oxygen 2 negative. This is going to break down to oxygen 2 negative.
The charge?
Are you sure? Now what happens? Isn't this, what is this here? Because remember, an acid is just an H plus. It's a proton donor. So it's always going to be that H plus. How many H pluses do we have since they put the H in front?
Three.
There are going to be 3 of them, right? And then what is going to be the other guy? Because look at this, HCl, right? We broke that down into H plus Cl minus, okay? Hydrogen sulfate, we broke that down into 2H plus and our sulfate. So what is this going to get broken down to?
Is it just ASO4?
That's right. And what charge?
Negative.
Just one negative?
No.
2 negative.
3?
3 negative. Now, don't forget what you learned, right? If you get 3 pluses, it got to balance it out with 3 negatives, right?
Yeah.
Yeah, don't throw everything that you learned in the beginning out the window. You got to keep it. We lost a few people. Am I boring?
I mean, I don't think so. I think you're being very clear about it.
Okay. Okay, so we got a few more things. Simple so far?
Yes.
Okay. Good. Let's go. Oops.
Actually, I think it was 10 from the beginning, so I don't think you lost anybody, but I don't know if that makes you feel any better.
Oh, there was 12 in the beginning.
Oh.
There was 12 in the beginning.
Oh, okay.
When I came on, there was 12.
Oh.
Or I guess 11. I lost one. So.
Well, I mean, like, if they can't handle the heat, then they, have to get out of the kitchen, right?
Exactly, yeah. Nice way of putting it. Okay, so this is the conventional way of writing the chemical equation, right? Now, what really happens, and this is what we're going to talk to you guys about, since we're talking about aqueous solution, what really happens is that these guys are in aqueous solutions. That means they're going to be breaking up into their ions. So if these guys are breaking up into their ionic components, what is this guy going to break up into? Since it's aqueous. Hold on one second. Somebody's knocking at my door. Okay, so let me rephrase this. Let me put it differently. So if these guys were dissociating, separating into their ions, what are the two ions that we're getting from lead nitrate?
It would be Pb 2+, and then it'd be 2NO3 2-.
That's right, 2NO3 2-. And you want to keep that AQ in there. Now, what about sodium chloride?
Would it be 2 Na plus and then 2 Cl minus?
Now, when things are solids, liquids, or gases, they're not going to separate. They're going to stay together. Okay? So you just want to write these down as they are. So I'll repeat that. When things are solid, liquid, or gas, we're going to leave them alone. And we're going to write them as they are.
So they don't break apart to separate ions, right?
That is correct. Now, what about the sodium nitrate?
That would just be 2 Na plus and then NO3 2-. And then the
would it be 2? Would it be 2? NO.
2, that's right. That's right. 2 NO3-.
Yeah.
Good job. Aqueous.
Why is it a 2 NO? Is it because that 2 and from the 2 NaNO3 does it distribute to both the sodium and the
nitrate? Yes,
right.
Because it's telling you that you have 2 sodium nitrates, right? So you're separating both.
Oh, yeah.
Just like over here, it told us that we had 2 sodium chlorides. Okay, piece of cake?
Yes.
Yes.
Okay, good. Okay, so now this here is called our total ionic equation.
What we just did.
Yep. Okay, total ionic equation. Conventional equation, total ionic equation. Simple so far?
I'm sorry, what did you say? I missed you pointing.
Conventional equation, total ionic.
Oh.
So what's the difference between the conventional equation and the total ionic equation?
They're essentially the same thing. The difference is that here we draw it as one compound together. But in actuality, this is what it really looks like. It's separated since they're ions. We're separating it into their ionic forms, right? Conventional equations, the ions are connected. Total ionic equations, we've broken everything apart.
Got it.
Do you see it? Are we here?
Yeah.
No, not really.
Pb2 plus, PbNO3. Does that look anything like each other?
Okay, so the example is a conventional equation?
This here is the conventional equation.
Oh, okay, gotcha. I thought that what we were doing before was the conventional, so I got confused.
No.
That makes sense.
No. This is the conventional.
That makes sense.
Conventional meaning what we normally do.
Yeah, like traditional or whatever.
Yeah, traditional, exactly. Okay, total ionic. Okay, now the net ionic equation is getting rid of spectators. Spectators are things that you see on both the product side and the reactant side that don't change at all. So for instance, I'm going to circle our spectators here. Maybe you guys can help me. Circle it in orange. Yeah, let's not use it. Okay, so we have PB2 plus. Do we see PB2 plus on the other side of the equation? On the product side?
No.
We have 2 NO3, 2 minus. Do we have 2 NO3? Sorry, that shouldn't be 2 minus, that should be minus. So do we have 2 NO3 minus over here?
Yes.
Okay, so let's go ahead and circle it. What about 2 Na plus?
Yes.
Okay, so the total ionic equation, net ionic equation is just what's left over after you get rid of the spectators.
I think I missed something because I was writing it down. So are the ones in green the spectators, or are the ones that, okay.
The ones that are circled are spectators. Have you ever gone to a party and you have that guy that comes to the party and he sits there and watches everybody but don't talk to anybody? Spectator.
Mm-hmm. Mm-hmm.
Mm-hmm.
Kevin, are you a spectator?
Yeah, I'm a spectator.
Okay. And that's it. Simple.
What does it mean by net ionic equation?
Net ionic equation is what's left over, right? The net overall, because the spectators aren't really doing anything. They're just bringing people to the party, right? And then the people that are brought to the party are hooking up, right? So you have PV hooking up with Cl. They get together, they leave together. Okay, where, you know, initially your spectators are just, hey, dude, come with me to the party, and they just sit there and not do anything.
So the ones that aren't spectators are doing more of the work, so that's why they're included in there. Okay.
Yeah, that's really what you're looking at. That's really what's happening in that reaction, right? Everything else, they're just going to be still in solution. They're going to be spectators. They're not going to do anything. Do you understand? So like the sodium and nitrate, they're not really there. They're just carriers. They're helping bring somebody to the party.
Oh, okay. Thank you.
Okay. Piece of cake? Not too hard?
No.
No.
Okay, good. Okay, clear. So when you're doing net ionic equations or just ionic equations in general, the first thing that you want to do is write down the right conventional equation, because if you don't, it'll screw everything up. And make sure that you include the state that everything is in, okay? It needs to be balanced, okay? So things to keep in mind, weak acids aren't gonna separate. And then solids, liquids, and gases don't form ions, okay? Okay, and the last thing is that you wanna make sure that at the end of the day, the equations is balanced. That's the number of atoms and also the charges, okay? And if you need to, you have to reduce to the lowest coefficient or lowest term. Okay, let's see, let's do this and then we'll stop here. Okay, when a strip of magnesium metal is placed in an iron 3 chloride solution, a magnesium chloride solution results and solid iron also forms. Develop the net ionic equation for the reaction. Okay, so what are my reactants? What is my conventional equation? See, Kevin, what are my reactants?
It would be FeCl3.
Solid, liquid, gas, or aqueous?
Aqueous.
Okay, what is it reacting with?
So it would be MgCl2, and that would also be aqueous.
Okay,
We're not doing the product side yet.
Okay, so then what is it reacting with then, if we're talking about the reactant?
You're asking me or Kevin?
I'm asking you.
It would just be magnesium then, right? Okay. And then it'd be a solid. I was just telling Kevin that so he would, just to help him.
Okay. So then our product is going to be?
Oh, I don't know the charges, but because I don't have my table in front of me, but I know what they dissociate into.
Well, before they dissociate, first we have to write the conventional equation. That's all we're writing right now.
Oh, okay. Oh.
So Kevin, what was our products?
It was MgCl2.
MgCl2. Solid, liquid, gas, or aqueous?
Aqueous.
And
then it's iron, which is Fe, and it's solid.
Okay. Okay, so now we're ready to dissociate. Okay, so over here, so total ionic equation. Total ionic equation. Cheyenne.
I had a question. Would we not balance the equation first or no?
That would be smart. Let's balance it. Is it balanced?
No.
Okay, so how can we balance it?
I would put a 2 in front of that. A 3 in front of MgCl2. 3 in front of Mg, and then a 2 in front of iron.
Okay, so now our total ionic equation.
2 Fe plus.
Is it 1 plus?
3 pluses.
Okay.
And then plus 2Cl.
Are you sure 2Cl?
Well, I know it's a -3 charge. Oh, so then is it 6?
Okay.
2, 6? Oh.
I have a question. So the iron would be a solid, right?
Nope.
Oh, okay. Why is the iron in aqueous? Why is it aqueous?
Because it's separating into its ionic components, which will be in solution.
Oh, okay.
Yeah.
I also have another question. I'm having issues like with identifying certain reactions. What kind of reaction is this?
This is a single replacement reaction.
And how do we know that when we're running out?
If you remember, we had talked about what a single replacement reaction is when you're replacing one component for another component. So it's like, I always say, like you're changing girlfriends, right? So here's your new girlfriend, iron's your old girlfriend. You're switching out magnesium for iron.
Yeah, I understand that, but like, how do we know, like, while we're writing out the equation that it's single replacement? Like, because if we're just
what's happening here? What are you doing?
Because it gives us the products. Sorry.
And even if it wasn't, I mean, what are you going to do? You can't replace chlorine. Isn't going to be replaced by magnesium because chlorine is a negative charge. So you only can replace a metal for a metal, right? You can't replace a metal for a non-metal. Do you know what I'm saying?
Yeah.
Okay. Oops.
And then it's 3 Mg2 plus.
Is it going to be 3 Mg2 plus? solid, liquid, gases, what does we do with those?
Well, they don't have an ion, so is it just a solid and no
That's right.
charge?
It's just that element. Yeah. Okay. On the other side.
Then we have the 3 Mg.
Oops.
Um, 2 plus since it's aqueous.
That's right.
I think I missed something. So why doesn't the Mg have the charge on it?
Does it have a charge here?
No.
It also has a solid on it. So how can it be broken down to an ion?
Okay.
And then it's plus 6Cl negative.
AQ.
Yeah, aqueous. And then 2 iron, and it's a solid, so no charge.
Okay. Okay, so next we're doing net ionic.
So this is where we take out the spectators?
Yeah, so that means we got to identify the spectators. Okay, we'll circle them in red.
So would it just be the 6Cl?
Okay.
Because if they have a charge, then they're not the same. So that wouldn't mean that they're a spectator, right?
That is correct.
Okay.
That is correct. Okay. So then we just are left with 2Fe, 3 plus, AQ, plus 3 Mg, S, yields 3 Mg, 2 plus, plus 2 Fe, S. Piece of cake?
Yeah, it's a little easier now.
Yeah.